a couple of new properties that you may have never heard of before. Right? Reflexive property says a value always equals itself. A value always equals itself. Right? A is always A. A is always equal to A. Right? So something like 5 is always equal to 5, or 3x is always equal to 3x. That's reflexive property. It's literally a reflection of itself. Literally a reflection. They're identical. Right? And then symmetric property says if A equals B, then B must also equal A. What does this mean? What does this mean? It's similar to reflexive in that they hold the same value, but it's different in that they can look different, right? So suppose you have 16, right, is equal to 4 squared. They are equal. They are both 16. They're symmetrical. If you put them on a balance scale, they will balance out because they're both 16. They're just not identical. This one's fun because there's about 1,000 ways to write the number 16 without actually writing a 16, right? 10 plus 6 is 16. Symmetric property says these are equal. So because they're equal, they can replace each other. We'll get to that. All right, and then the next one, transitive property, is intense. Brace yourself. All right, transitive property says if A equals B and B equals C, then A equals C. Think about the word transit. It means to travel, right? Transit, like a bus, right? So basically they're saying, let's use another number, not 16 this time. Let's do 9. If A is equal to B, 3 squared, right? And 3 squared is equal to 27 divided by 3. If A is equal to B and B is equal to C, then A is also equal to C. And to be transitive, it has to have at least 3 different terms, right? It has 3 terms. 1, 2, 3. 3 terms that are all equal, equivalent, but they all look different. Transitive property says you could have 15 different terms, but you have to have at least 3 that are equivalent, meaning equal, but look different. Right? Symmetric property says 2 terms that are equivalent or equal, but look different. And then reflexive property says they have to look identical. They have to be a reflection of each other. Right? We'll play with this one a little bit in class because I think the idea that we can create something like 50 different ways of writing the same value might be fun. All right, let's look at the idea of closure property, right? Closure property says a set is closed under an operation. We're talking about addition, subtraction, multiplication, and division. A set is closed if the operation always produces an element of the same set. So if you add 2 numbers and can only get another positive number, that's closed. If you have two negatives and you can only get another negative, that's closed, right? So if an element outside the set is produced, then the operation is not closed, right? So in this case, integers, let's remind ourselves what integers are, right? They're the number line numbers, right, are closed under multiplication, right? So if I multiply any two integers, do I still end up with an integer? Yes. There's no possible way to multiply two integers and end up with a decimal or a fraction. It's impossible, right? So this is closed. This is true. This is true. Integers are closed under multiplication. If you multiply two integers, you will always get another integer. Natural numbers are closed under subtraction. Natural numbers are your counting numbers, right? So if I subtract two natural numbers, am I always going to end up with a natural number? No. No. And if you're going to say something is false, you have to come up with evidence, right? So what two numbers of these, just from this little example, what two natural numbers can I subtract and end up with a not natural number? A not natural number would be 0 or negatives or decimals or fractions, right? So if I did 2 minus 4, I would end up with negative 2. Negative 2 is not natural, right? So you can subtract two natural numbers and end up with a number that's not natural. So this is not closed system. This is false. Even numbers are closed under addition. Even numbers, 2, 4, 6, 8, and anything that ends in 0. These are your even numbers, right? We're looking at addition. If you add any two even numbers, you will always end up with another even number. Think about that for a second. Can you come up with an example where you added two even numbers and ended up with an odd number? No. This is closed because you add two even numbers, you will always get another even number. Right? And then irrational numbers are closed under division. Okay, we're looking at the operation of division, and we're looking at irrational numbers. So let's just use pi, because it's our favorite, or my favorite, because pi. Is it closed under division? Is there something I can divide this by to create a rational number? Yes, because anything over itself equals 1, and 1 is a rational number. So your evidence is pi over pi, which is equal to 1, and this is not irrational. So it is not closed. False. Perfect squares are closed under subtraction. First we need to know perfect square, and then we need to look at them under subtraction. Perfect squares are the numbers you get when you multiply a number by itself. So 3 times 3 is 9, so it's a perfect square. 4 times 4 is 16, so it's a perfect square. 5 times 5 is 25, so it's a perfect square. Why do we call it a perfect square? I'll tell you why. If you draw a square and you say that this side is 5 and this side is 5, 5 times 5, you've got a perfect square. They are the same side length all the way around. They are all 5s. It is a perfect square. Thus, that's why it's called a perfect square. So, perfect squares are closed under subtraction. So if I subtract two perfect squares, does it always end in another perfect square? Let's just pick two random perfect squares. What is 25 minus 9? 25 minus 9 is, what is 25 minus 9? 16? Is 16 a perfect square? Yeah. Let's try another one. Let's do 25 minus 2 times 2 is 4, so let's do 4, because 4 is a perfect square. 25 minus 4 is 21, not a perfect square. All you need to do is find one example to prove it wrong, and then it's false. One example to prove it wrong. All you need is one example to prove it wrong, and then it's false. This was our example for rational numbers. This was our example for perfect squares. All you need is one example to prove it wrong, and it's false. So, integers are closed under multiplication. Natural numbers are not closed under subtraction. Even numbers are closed under addition. Irrational numbers are not closed under division. And perfect squares are not closed under subtraction. I know this is new information. Take a second, think about it. See if you can prove me wrong. Free grade to anyone who can prove me wrong on these points. That means you actually have to think about it. Alright, and like I said with the last video, my suggestion is that you get the practice sheet, you attempt it on your own, and then you go back and watch the video to check your work. It doesn't do any good to watch the video first, because then you're not doing the work on the practice sheet and you're going to fail the mastery check. Watch the video after you attempt it. And that way you can see, hey, I was right, or hey, I was wrong, and this is why I was wrong. It'll be a lot more helpful that way.